On this part of the video, we will talk about diffraction gratings. When you have a large number of equal spaced parallel slits, those are called diffraction gratings. Gratings are often made by ruling very fine lines on glass with a diamond tip. The space between the lines serve as slits. Gratings contain a huge number of slits per centimeters, usually is over 15,000 slits, and a double slit equipment, if the double slit equipment produces an interference of the pattern where the fringes tend to be broad and relatively undefined, diffraction gratings produces a very sharp and very well defined bright fringes and dark fringes. Okay, so I will show you a video in class in regards to the different colors that are in different colors that have diffracted by different amounts. Interesting enough is that a diffraction grating is managed by the same formulas as the diffraction and interference that we saw on the previous video. So lambda is equal to d sine theta over n, or lambda is equal to d x over nl. And now we know what d is the distance between the two slits. Angle theta is the angle created between the two imaginary lines, one that goes perpendicular bisector of the distance between the two and the screen, perpendicular to the screen. And the line that connects that point, the midpoint of the distance, with the fringe, whatever you have, bright or dark fringe. And the other formulas are d is equal to lambda, or is equal to d sine theta over n minus 1 over 2, and dx n minus 1 over 2 times L. The first one are used for constructive interference, in which they are producing bright fringes, and the second group, this group here, is used when we have deconstructive interference. On those formulas, what we have is d is the distance between the two slits, and then we know x is the distance from the central fringe to the fringe that we are looking at, and L is the distance from the slit to the screen, and everything has to be in meters. Now, what do we have is in the diffraction grating, since we have those lines that are parallel to each other, that are like a large number of lines parallel to each other. Now that d, the way that we calculate d at the diffraction grating is that we calculate it using those two steps. So if we have the number of lines, let's say that we have 5,000 lines per centimeter. Okay, so what do we do is, as a very first step, we find the number of lines on a meter. Okay, so now if we have 5,000 5,000 lines in 1 centimeter. We convert it into meters, so we will have 100 centimeters into 1 meter. And then as a result, we will have 3 zeros and 2, 5. So 500,000 lines per meter. If the question is giving you the lines per meter, then you will skip this first step and then you will go straight to step 2. In which when you are finding the distance between the 2 slits, is you are just inverting it. So D will be 1 over the number of lines, I will say it here, number of lines per meter. In our case, D will be 1 over 500,000 lines per meter, which means so that it is 2.0 times 10 to the power of -6 meters, the distance between the 2 lines. So this is the only addition to the formula that we have for diffraction and interference. And so if we have a question in which the diffraction grating is given, then we still will use the same formulas. If they're asking for the angle or the angle is given, then you will use the first formulas, depending if it is a bright fringe, we'll use this, and if it is a dark fringe, then we will use n minus 1, -1 over 2. Sorry, -1 over 2. So we have here a monochromatic light. Monochromatic means that we have a light with 1 wavelength. So not a white light that all the colors are there, but it's just 1 wavelength. And we have a diffraction grating of, so diffraction grating of 10,000 lines per centimeters. And they are producing an antinodes, meaning a bright, okay? So antinode, bright fringe with an angle of 40.5 degrees on the first one. So n equal 1. What is the wavelength of this monochromatic light? Then, well, first we will figure out what is the distance between the 2 fringes. So we'll have 10,000 lines per centimeter times 100 centimeter into 1 meter, which will give us lines per meter. And then to find D, we go 1 over the number of lines. So okay. And we will have 1.0 times 10 to the power of -6 meters as the distance between the 2. And now we have to decide which formula are we using. Are we using sine theta, d sine theta, or d sine theta over n? And since we have bright, we are not going to this group of the formula, but we are just using one of the two, this one or this one. And since the angle is given, then we use the sine theta one. So lambda will be, or the wavelength will be d times sine theta over n, or 1.0 times 10 to the power of -6 times sine 40.5 degrees over 1. So the wavelength is 649 nanometers, or 6.49 times 10 to the power of -7 meters. So always when you have this monochromatic, means that it is one wavelength. Let's take a look at another example here. So when we have monochromatic light that has a diffraction grating of 10,000 lines per centimeters, is producing an antinode at 65 centimeters off the center of the line on the screen that is 100 centimeters away. So let's sort what is given. It is 65 centimeters is the same as saying 65 times 10 to the power of -2 meters. And then we have L as 100 centimeter. So this will be 1 meter. But as you see here, the distance between the two, it's not, it is, they are very close to each other. 65 is not way smaller than 100 centimeters. So therefore, what we have to do is we have to find the angle theta that is between them and then use the formula. Okay, so the sine formula. But before we do that, let's find the distance. Since it is the same calculations as before, it is 1 over lines per meter, giving us 1.0 times 10 to the power of -6 meters as the distance between the two. And now, how will you know if that is something that you have to avoid? Using the formula, you have two formulas to use. Lambda is equal to d sine theta over n, or lambda is dx over nl. Now, one thing is when you see that x is very comparable to the L, it's not way too smaller. This formula, it's true only when x is too smaller in comparison to L. So the screen is far away from the source, and the distance between the central and the fringe is smaller. And another thing is you will see if angle theta is less than 10 degrees, because if it is more, then tangent and sine are not close to each other. So now, based on the geometry that you have here, is 0.65 meters. Sorry, it's opposite. 100 centimeters and 0.65 centimeters will produce an angle that is an angle theta here that is using trig ratios. Will be angle theta is the inverse tangent of 65 over 100, which will be 33 degrees. So it is greater than 10 degrees. So two are the things that will make you believe that this is something that you should not go and use the lambda is equal to dx over nl. Now that we know the angle theta, we can use the other formula as lambda is equal to d times sine theta over n. And n is equal to 1 since we are dealing with the first order of antinode, and we are not taking 1 over 2 away from n because we are not dealing with nodes. We are dealing with bright spot fringes. So this will be 1.0 times 10 to the power of negative 6 times sine of 33.0 degrees over 1. And then the wavelength is 5.4 times 10 to the power of negative 7 meters. Okay, so compare the distance between the L and X in order to figure out what is the right formula. But in general, is if they're asking for the formula for the angle or the angle is given, then use the angle formula.